Hi, I'm Tim Holme, co-founder and chief technology officer of QuantumScape, and I'm here to talk to you today about stability in the context of batteries. So first of all, in case I say anything that speculates at all, please visit our disclaimers on the SEC website where we've listed all of our risk factors. So at QuantumScape, we are developing lithium metal anode batteries for the simple reason that it's the single biggest change that you could make to improve the energy density of a battery. So this is an analysis done by BMW several years ago that looked at a number of different cathode active materials on the x-axis and the energy density that they believe that a reasonable cell could attain on the y-axis, watt-hours per kilogram. And so what's apparent is if you use today's graphite anodes, the energy densities are rather limited. What's coming in the future is mixing in increasing amounts of silicon into the anode, which gives you certainly energy density improvements. But it's not until you delete the hosted anode material entirely and move to a lithium metal anode that you can unlock very high energy densities. And this is true for oxide, NCA, NMC type cathode active materials, as well as some more advanced next generation, potentially cathode active materials. And one thing that we've come to understand or believe at QuantumScape is that a lithium metal anode is very difficult to use without a solid state separator. So this is a schematic on the left of a lithium ion battery with the 5 key layers, an anode current collector that brings the electrons and heat in and out of the anode side of the cell, the anode or negative electrode, which has graphite and or silicon or a mixture of those two to host lithium when the battery is charged, a porous polymer thin separator that separates the anode from the cathode, a cathode electrode with cathode active material particles that store the lithium when the battery is discharged, and an aluminum current collector. The QuantumScape approach is to remove the anode host material and replace it with nothing as manufactured. All the lithium in the cell comes in the cathode active material and it plates on the first charge through the solid state separator and forms an in situ lithium metal anode. And then to enable this, we've replaced the porous polymer separator with a solid state dense ceramic separator. So this has traditionally been hard, and the reason that you can't go out today and buy a solid-state battery is because historically solid-state batteries have been unable to satisfy simultaneously the requirements that are important in an electric vehicle. So for an EV market, a good start, I would say a necessary but insufficient condition of performance requirements is a simultaneous test of charge current density, which translates to how fast you could charge a car. We believe that at least a 1C average rate or around what you can get at a supercharger today is required. That 1 hour rate is called 1C. You would need a cycle life of at least 800 cycles. 800 cycles for a 300-mile range car would translate to 240,000 miles over the lifetime of the car, which is longer than most people drive a car. The car would need to be able to operate at room temperature and even well below room temperature. Historically, many solid-state batteries have been limited to operating at high temperature only. A commercial solid-state battery, we believe, should be anode-free so that there's no extra cost, volume, and mass and safety implications of using a lithium metal anode. There should be at least a modest cathode loading of 3 milliamp hours per square centimeter or more. This is the cathode thickness. The cathode really is what stores the energy in a cell like ours. So you want to maximize the thickness of cathode with respect to the thickness of all the other inactive layers to maximize the energy density of the battery. And so a range of about 3 to 5 milliamp hours per centimeter squared is reasonable. At least 3 is necessary for an energy cell. And another limitation is pressure. Solid-state batteries typically have needed to apply some pressure to keep the layers in good contact. Even a lithium-ion cell will operate under a modest pressure at the beginning of life, and then it'll swell and the pressure grows towards the end of life. But the car module would have to apply pressure to the cell with some mechanism, for example, a clamp or a fixture to apply pressure to the cell. And that pressure fixture would have extra mass that if the pressure gets to too high of a level would be a mass that makes the commercial solid state battery unattractive. So somewhere in the range of single digit atmospheres, call it below 5 atmospheres, would be reasonable for pressure to be applied in a commercial application. But pressures like 10, 20 or higher atmospheres have such a large pressure fixture to apply that pressure that it's really not practical in commercial automotive applications. So a simultaneous test of demonstrating all 6 of these in one cell or in a batch of cells, but in a batch of cells that are tested under these conditions simultaneously is a good starting place to say that you have a promising technology. It's not a sufficient condition because a car would have to meet other requirements like low temperature operation, even faster fast charge, drive cycles, longevity, and so forth. But this is a good start, and many solid-state batteries have been unable to meet it. But here we show data showing that our cells are able to pass this simultaneous test. So what we're showing on the y-axis is the energy retention of groups of cells made and cycled under the conditions shown in the table. So 1 hour average rate of charge and discharge, at least 3 milliamp hours per centimeter squared of cathode loading. That when charge and discharge at 1C, that translates to a current density of over 3 milliamps per square centimeter. These were all tested at 25 to 30 degrees C, so very close to room temperature, with an anode-free lithium metal anode at full depth of discharge over commercially relevant areas, modest pressures. And then what this chart overlays is results on 1-layer cells that we released about a year and a half ago, 4-layer cells, 10-layer cells, 16-layer cells, and third-party testing of our single-layer cells, where all the curves lie essentially on top of each other, meeting this performance requirement of more than 80% energy retention to 800 cycles. We've also since then released some data showing that cells can cycle with 0 externally applied pressure. So these are single-layer cells where the cycling conditions are as shown on the previous slide, except for that we apply no pressure to the cell. So we construct a single-layer pouch cell that has 1 cathode, 1 solid-state separator, 1 in-situ formed anode. We put this into a pouch cell. The pouch is the material that holds the cell. It's material like what you buy coffee grounds in. We evacuate the inside of the pouch, so there's vacuum inside. Then we seal the pouch, and when these are tested, they're tested with no test fixture. So there's no external pressure application mechanism other than the ambient pressure you get in a room at sea level. And so what's pretty interesting, I think, scientifically, is a demonstration that lithium metal anode can be made to cycle at high rates, 800 times with no applied pressure. We've also talked about fast charging. So this is a plot showing the state of charge that can be attained when charging a cell over time. And the gray curve is what you would find if you plug into a supercharger. We set for ourselves the commercial target of charging 10 to 80% in 15 minutes. And this is a charge curve demonstrating that a single layer cell of ours can meet this requirement. But then we've gone further to do repeated fast charge cycling. So this is a chart showing groups of our cells at room temperature, 25 degrees C and 45 degrees C, cycling with a fast charge on every charge and a 1C discharge, so relatively fast discharge. This is a very aggressive test. Imagine charging up your car faster than a supercharger could charge your car up today, and then driving it basically as fast as you can on an Autobahn to fully discharge a long-range battery electric car in 1 hour, and then turning on repeating that 15-minute fast charge and repeating the 1 hour discharge, doing that over and over and over for 400 times. And what we're showing is that groups of our cells, again, single-layer cells, can meet this test also. So while we work on incorporating the improvements and the learnings we've made on single-layer cells at fast charge and zero pressure into our baseline, we've also now want to turn to the topic of stability. So in our third-party testing, there was a measurement of Coulombic efficiency. This is a measurement from that third-party test lab of the Coulombic efficiency of each cycle. Coulombic efficiency is the charge efficiency of the cell. So how many charges do you extract when you discharge the cell versus how many electrons or how many coulombs, how many milliamp hours do you put into the cell when you charge the cell? And so a perfect cell would operate at 100% Coulombic efficiency forever. What we're seeing is fluctuations around 100%. This is basically due to temperature fluctuations or the limitations of actually the accuracy of the test equipment, because the accuracy is, we're getting to the point where the cells are at least as coulombically efficient as the test equipment can measure. But then if you average the Coulombic efficiency across these cells across their lifetime, you see an average of about 99.99% Coulombic efficiency, which is high. It's also required if you're going to cycle with long cycle life, a lithium metal-free cell, because we're applying no excess anode lithium that could be consumed during the cycling. So what would be the Coulombic efficiency requirement? If the automotive requirement, as we've discussed, is 800 cycles, and which gives you 240,000 miles for a 300-mile range car, then you could just simply calculate what Coulombic efficiency is required to get a certain cycle life with a certain amount of excess lithium. So some strategies that do apply excess lithium would apply it with an evaporation process or a lithium foil, both of which would be expensive. Very thick excess lithium, like call it 70, 80 microns, would then dilute the entire volumetric energy density benefit you would get relative to a graphite anode. So then just zooming in on the 0 to 50 microns of an excess lithium layer in the anode, the more excess lithium that gets applied, the lower Coulombic efficiency that can be tolerated from the standpoint only of lithium capacity. I'm not talking right now about electrolyte. Let's assume there's excess electrolyte that can be reacted with that lithium. If 50 microns of excess lithium is applied and a cycle life of only 300 cycles is desired, then the Coulombic efficiency needs to be about 99.1% approximately. But as the amount of excess lithium is reduced into more and more attractive regimes, the Coulombic efficiency requirement grows. And then similarly, if the cycle life requirement grows from beyond, say, consumer electronics or drone applications up towards automotive applications where longer cycle life is required, then also the Coulombic efficiency requirement is increased for any given amount of excess lithium. And so if you come down to the lower right part of this graph with 0 excess lithium and 800 cycles, that is the requirement, well in excess of 99.9% Coulombic efficiency to endure 800 cycles. And just then to elaborate on the point of excess lithium, well, the excess lithium is expensive. Either pressing a lithium foil down to be quite thin or using a vapor deposition process to deposit thin lithium is expensive. It then poses potentially a safety risk in the factory when you're manufacturing the cell with metallic lithium, which is a very reactive compound. But also in the field, when the cars are driving around with excess lithium, suppose there's a crash, the excess lithium on the anode has extra energy that could be liberated in the crash. Excess lithium also adds some processing and scaling complexity. It requires excess solvent and salt to react with that lithium, because when the lithium reacts in a Coulombic efficiency less than 1, it's reacting with something, typically the electrolyte and salt. Then these reaction byproducts that form increase the impedance of the cell. So for all these reasons, excess lithium and low Coulombic efficiency is undesirable. So Coulombic efficiency well in excess of 99% is required. And just to note, for these calculations shown in the graph here, I'm assuming about a 4.1 milliamp hour per centimeter squared cathode, which is in the range of what's commercially viable for an energy cell. So why is Coulombic efficiency of 100% hard to achieve? Well, lithium is the most reducing element that there is. So this is the periodic table with standard electrode potentials of reduction shown for each element. The more red an element is, the more reducing it is. And lithium is the top left element here that's shown in the darkest red color at minus 3.04 volts. So it is the most reducing element. The other groups in the family are nearly as reducing, but lithium is the most reducing element. This is one reason, by the way, that it makes for a good battery. A battery has to store a lot of energy, so there has to be a lot of energy liberated when the anode and cathode active materials react with each other. So you need to make a battery out of reducing elements on one side. And then also, lithium is high up north on the periodic table. That means it's light. So a good battery should have high watt hours per liter and watt hours per kilogram. You do that by reducing the kilograms and maximizing the watt hours. So that basically means that you're incentivized as a battery designer to work with elements like lithium that are very reducing. But because it's so reducing, it's very hard to find materials that are stable in contact with lithium over long periods of time. So for example, a car should be running well for at least 10 years, 12 years, 15 years, something like that. And then if you look at solid-state electrolytes, most solid-state electrolytes are not stable in contact with lithium, unfortunately. So this is a plot similar to what we were making at QuantumScape in 2013. This is a plot from the public literature. The Gerd-Cedar group in 2016 studied a lot of materials, families of sulfides, hydrides, oxides, and halides, and showing the stability window. So stability window extends from the left part of a bar over to the right part of a bar. The left part of a bar shows where the material would tend to get reduced, and the right part of a bar shows to where the material would thermodynamically tend to get oxidized. The ideal solid-state electrolyte would be something like lithium fluoride that has a very wide stability window that extends all the way down to 0, meaning it's stable in contact with lithium, and then all the way up above 4 volts to where the cathode reacts. Unfortunately, lithium fluoride doesn't have sufficient conductivity to be a lithium electrolyte. So all of these other materials that are then shown that are lithium electrolytes don't have stability windows that extend all the way down to 0. Some of the most common solid-state electrolytes are highlighted in these arrows here. There are phosphates like LATP, LAGP, oxides like LLZO, the whole family of sulfides that have very narrow stability windows. I'm overlaying on top of this graph some of our calculations of stability windows of other materials that weren't in this publication, but this is an LLTO perovskite and some other of the halides that are now being studied for lithium-ion conductivity. What you can see is that these materials that I've highlighted don't have stability windows that extend all the way down to 0, so they're not predicted to be thermodynamically stable in contact with lithium. And this raises kind of a fundamental quandary illustrated in this graph here. I'm just taking binary compounds of lithium, nitride, sulfide, oxide, and fluoride, and plotting the activation energy for lithium to diffuse through the material on the y-axis and the energy of formation on the x-axis. So the x-axis indicates how stable is the material as formed. Further left is more stable. There's more energy released by the reaction to form the material. That is, it's a more stable material. And further down on the y-axis indicates a material where lithium hops through the structure more readily. So a sweet spot for a solid-state electrolyte would be in the bottom left corner here, with a material that's both very stable and lithium moves through readily. And unfortunately, what you can see is this trend where more stable materials like lithium fluoride bind lithium more tightly. This is no accident. They are more stable because they bind lithium more tightly. That makes lithium harder to hop through the structure. And on the other extreme, lithium nitride binds lithium very weakly. It has a low activation energy. It's actually a very good lithium-ion conductor, but it's not very stable because it's indicating it by its place over on the right of the chart. Other things tend to correlate with vertical and horizontal placements on this chart. For example, the electron resistivity or band gap the band gap tends to be higher for more stable materials. So materials on the left tend to be more ordered, more stable, have higher band gaps, have therefore higher electron resistivities, which is also a good parameter for a solid-state electrolyte. The electrolyte, again, is a material that conducts ions but not electrons. So if it does conduct electrons, that's a problem. There's an internal short inside the battery. And materials over on the right tend to have more lithium mobility, more disorder, more electron conductivity. They tend to be darker or more opaque materials because of that low band gap. But unfortunately, this is kind of a pretty much a fundamental quandary that confronts a solid-state electrolyte designer, that materials don't tend to fall down in this sweet spot because the stability is sort of roughly empirically inversely proportional to conductivity. So, and of course, a solid-state electrolyte should have both high stability and high conductivity. So it's a difficult problem to solve. Well, of course, in a lithium-ion battery, the electrolytes are not stable to the anode potentials either. There's this concept of kinetic stability or passivation, which has been known for a very long time. This is a plot from Emmanuel Peled, who is studying SEIs way back since the 70s, where he described this SEI model, solid electrolyte interface, that's produced when a lithium-ion electrolyte breaks down on a lithium or carbon anode. It forms all of these other materials like lithium fluoride, lithium oxide, lithium carbonate, and then as you progress further into the SEI, less stable materials like polymers, polyolefins, etc. So lithium-ion batteries don't operate in a regime of thermodynamic stability, they operate in kinetic stability. So this concept could be applied to solid-state batteries as well. So there have been studies such as this one done by the Yannick group that study the passivation processes on this particular study was done on 3 popular solid-state electrolyte materials, an LLZO, a sulfide argyrodite compound, and a glassy phosphate LATP. The greenish region of these plots indicates a regime where lithium has reacted with the solid-state electrolyte and formed a material that's neither lithium nor solid-state electrolyte when placed into contact. So in the left-hand side, what you're seeing is a contact between lithium and LLZO, and showing that there's a relatively sharp interface with very little transition region between the lithium and the solid-state electrolyte. The middle plot on the sulfide argyrodite compound shows lithium and then this interfacial region and then a solid-state electrolyte. And the right plot shows that in LATP, there is essentially full reaction between lithium and LATP. So this is not a passivating reaction. I think a lot more study needs to be done on the kinetics of passivation. One, it is developing, but one interesting question I want to point out is that this interfacial reaction regime was measured to be about 250 nanometers in this paper. 250 nanometers is well above a tunneling distance of electrons. So if this reaction can grow to 250 nanometers, that means it's conducting electrons to some extent and conducting lithium ions to some extent. So if that's the case, then one would expect this reaction to continue. Maybe it slows down, maybe there's a square root of time dependence or something like that. But I do believe that more theoretical developments here in terms of understanding of kinetic passivation would be beneficial to both understand the mechanisms at play in solid-state batteries and optimize the materials discovery process. So we've talked so far about the low voltage challenge or stability towards lithium. There's also a challenge in high voltage. So liquid electrolytes have well-known stability challenges that have been well documented by many of the researchers in the field. And the stability challenges get worse as higher and higher voltages are achieved in the cathodes. As this plot, which is similar to the plot we showed earlier from the Cedar group, this is another plot from a paper in 2019 from Yifei Mo's group, showing that again there are high voltage stability challenges for most of the classes of electrolytes. So this result corroborates with the earlier papers, showing that oxides will tend to evolve oxygen above around 2.9 volts or so, which is the open circuit voltage of reaction of lithium and oxygen. Sulfides would have a driving force for sulfur oxidation above 2.4 volts, which is where lithium and sulfur would react. And the halides would have driving forces for decomposition above about 3.6 or 4.2 volts. And that's roughly what this chart shows as well. There are some first order modifications to this. I would say this is a 0th order model, these voltages given here. The first order modifications are what are the other elements involved? What is the crystal structure? That's what this chart shows here. Nevertheless, it does show that for the most popular classes of solid-state electrolytes, the thermodynamic predictions are that they would be unstable to 4 volts, where cathodes would want to operate. Another way to illustrate the challenge and the magnitude of the challenge of high voltage stability is to just look at the Inerts equation, which is given right here, which takes the ratio between the activity of the oxidized species and the reduced species. Think about this as the anode and cathode activity, so the activity lithium would have at the anode and the cathode. In the Inerts equation, that tells us it's exponentially related with the voltage difference of the anode and cathode. And there's also a temperature factor. So then this table shows that activity ratio calculated at 25 degrees C for different operating voltages of the cell. So this is assuming a solid-state electrolyte is in contact with the anode and cathode on either side and has to be stable on either side. So if the operating range of a battery is 0 to 4 volts, then the lithium activity is different by 67 orders of magnitude from the anode and the cathode. That's a large number, but of course gets even larger if the cathode voltage is increased to 4.2 or 4.5 volts. this is why, or one reason why SEIs tend to form, because very few materials are stable across such a wide voltage range. So then they need to break down and passivate and form a layer that limits the voltage that it will be observed. If an SEI layer and a CEI, a cathode interface layer, form, then the activity range can be potentially reasonably achieved with known materials. So SEI and CEI layers are likely to form even in solid-state systems. So a few comments on how experimentally, this was all theoretical or computational background, a few comments on how experimentally to measure stability windows. Cyclic voltammetry or linear sweep voltammetry tends to be a very popular method, maybe the most popular method to measure the stability of compounds in an electrochemical context. So just to illustrate that, here are the number of Google Scholar hits over time for this search shown with cyclic voltammetry, lithium battery, and stability. So you can see that this is a very fast-growing field. I've done some linear extrapolation for the rest of the 2021 to 2025 timeframe, showing that this linear on a logarithmic scale, that is an exponential relationship, has been roughly holding over the last few decades with a doubling time of around every 6 years. That doubling time is not important, but what is important is that a typical experiment for cyclic voltammetry involves a working electrode, a counter electrode, and an electrolyte in between them. This working electrode is swept with respect to the counter electrode over a voltage range, and the current is measured. So what's typically done is there would be planar interfaces of each electrode to the electrolyte, often platinum or glassy carbon. Often the electrodes that are selected for their inertness. Which is interesting because in a battery application, there will be high surface area interfaces, not planar interfaces, and they would be reactive materials, not inert materials. A typical linear sweep voltammetry or CV would use what I would call a fast scan rate of between 0.1 to 1 millivolt per second. There would be few scans, either only one scan or a small number of scans over this voltage range to see how the stability evolves over cycles. And there would be little quantification because it's hard to identify the onset voltage of reactions. I would go so far as to say, in my personal opinion, it's an ill-defined problem. It's also hard to see these small parasitic currents that need to be studied when you're studying stability. So just to expand on those points a little bit, here are 4 different measurements of the same system. I took the same electrochemical system and in our labs did linear sweep voltammetry to measure the current in response to the voltage across the working electrode. And the first point I want to make is that the current that you measure depends on both the scan rate, which was taken to be 0.1 millivolt per second in these 2 cases, and 10 millivolts per second in these 2 cases. It also depends on temperature. I chose 60 degrees C to accelerate reactions and 30 degrees C as a number near room temperature. What you can see is that cyclical voltammetry response depends on these conditions pretty sensitively. That's one point to make. But the second point to make is that the system I was measuring here was actually lithium with typical carbonate electrolytes, ethylene carbonate, DMC, and LiPF6 in a cell guard separator. Well, of course, those of you who've worked in batteries and electrochemistry know that aluminum foil is not an inert material towards lithium. Lithium should alloy with aluminum at around 0.4 volts, yet that alloying reaction is not really visible on this chart around 0.4 volts. You'd also expect the liquid carbonate electrolytes to start breaking down and forming SEIs somewhere around 1 volt or 1.5 volts. And no trace of that can be seen on the cyclic voltammetry. So this is starting to explain a few of the limitations of a CV measurement. To go a little bit further into the theory of cyclic voltammetry measurements, the lithium deposition kinetics that you would measure around 0 volts actually must be many orders of magnitude faster than any parasitic reaction in the battery. And graphing them on the same y-axis masks the very important stability-related signals that one would be looking for. So let's quantify that. In lithium plating, the current that would run when lithium is plated is related to the overpotential applied divided by the resistance. So this is just Ohm's law when units are normalized by area. So current density that you would measure in a cyclic voltammetry proportional to a voltage divided by a resistance. So a typical measurement might apply about a half volt or so of overpotential. A cell to run well should have around approximately, on the ballpark of 10 ohm centimeters squared. This is just the back of the envelope calculation. Feel free to do your own calculations and plug in different numbers. You should still likely reproduce the same orders of magnitude that I'll find. Anyway, that current density that you would find is just by dividing the two numbers is 50 milliamps per centimeter squared. Well, so that is the lithium deposition kinetics that a good battery should have. Then let's talk about the parasitic reactions that could be measured with a cyclic voltammetry. I'll talk for both reversible and irreversible side reactions and use some of the equations that you could find in an electrochemistry textbook like Bard and Faulkner. So for reversible reactions, the peak current that you would find in a cyclic voltammetry is given by this awful equation. I'll make it simple for you and do the math, plugging in some reasonable numbers for the scan rates, the concentration of species, the diffusivities, and what you'll calculate is the peak current that you would measure is 30 microamps per square centimeter. In a minute, we're going to compare this 50 milliamps per square centimeter to 30 microamps. But first, let's just look at the math for irreversible reactions. It's a little bit different equations. It turns out you get similar order of magnitude peak currents that can be measured in cyclic voltammetry. Here, the answer happens to be about 16 microamps per square centimeter. So to compare these two numbers, you get about 3 orders of magnitude difference between the desirable reaction of lithium plating and the undesirable side reactions that could be measured in cyclic voltammetry. So maybe you'd say, okay, cyclic voltammetry is only a factor of 1,000 off of measuring stability in a real-world system. However, I'm going to argue it's worse than that. What sensitivity is required to measure real-world stability that would be sufficient for batteries to operate in the field? So first of all, let's calculate an interfacial area factor. I mentioned that most cyclic voltammetry is measured on planar electrodes, whereas in a real battery, there will be high surface area electrodes. So this surface area will give you an enhancement depending, again, on the assumptions you make and the design of your battery of about 10 to the 2. This is then considering only the cathode active material. I'm ignoring anode active material and the carbon conductive additive. Then there's another factor that relates the rate capability of a battery versus the impedance growth that a battery is allowed to have over its life. So let's say a battery, just to pick some numbers, has to operate at roughly 2C rates. It needs to have high enough conductivity to deliver lithium, 100% of the lithium across the cell at a 2C rate. So how much lithium flux is that? 100% of the lithium in the cell in half an hour. That's the rate of lithium transfer. A parasitic rate of lithium reaction, let's assume that you will allow 10% of the available lithium in the cell to react over a 10-year life of the battery. So then you have 10% of lithium over 10 years. Work that out to an order of magnitude, that's about 1.8 million. So about an order of magnitude of a millionfold. So these two factors multiply together to give you the type of sensitivity you would need in a planar CV. You would need a factor of 10 to the 8 sensitivity in cyclic voltammetry. However, we just established on the last slide that CV would only be able to measure a factor of 10 to the 3. So there's a fundamental gap here. So I would argue that cyclic voltammetry is not the right measurement for lithium stability. So we did a pretty deep dive here. Hopefully you all got something out of it. The takeaways here are to achieve a high cycle life in a practical application requires a high Coulombic efficiency, which requires a very passivating anode interface. And to measure real-world stability in the real world requires much more sensitive measurements than linear sweep voltammetry or cyclic voltammetry to demonstrate stability and passivation. So I'm encouraging the community of all of us battery researchers to take these points on board when we're considering how to test, evaluate, and design batteries for stability over long lifetime. So this is a very difficult and challenging field. It's very rich. There's a lot of areas to understand and improve. Our team at QuantumScape is engaged in this right now and also looking for other talented people who are inspired by these types of challenging problems that could have real-world impacts.